Hello, this is Ben Greenman speaking, and I'm here to tell you about our team's recent work. Over the past few years, we have developed and evaluated a method to measure the performance of a gradual typing system. The method is a tool for language implementers to understand the performance implications of a design choice and to systematically compare different implementations of gradual typing for the same underlying language. To begin, let's see why performance is an issue for gradual typing. In any programming language, we can picture a program as a collection of components. Some components may depend on others, and at runtime, values may cross these dependency edges. In a gradually typed language, a developer is free to make some components statically typed and other components dynamically typed. Static and dynamic components may depend on one another, and in this case, we call the edge between them a type boundary. A type boundary is a channel of communication. For example, a typed component may request an integer and receive the untyped value 42. In this case, the type and value happen to match. In general, if we care about maintaining a relationship between static types and runtime values, then we need to watch for possible mismatches. For example, a typed component may ask for an integer and receive the untyped value nan. In this case, we need a check to detect the mismatch. These safety checks impose a runtime cost. The size of the cost depends on the interaction. If a typed component expects a list, it may need to traverse the given value to identify a mismatch. If typed code expects a function, it may choose to wrap the given value in a proxy that monitors the behavior of the untyped function. The bottom line is that type boundaries lead to a non-trivial runtime cost. And so, for a program, we would like to understand its performance, and for a gradual typing system, we would like to understand its performance implications. For this, we need a systematic method. Our method starts with the acknowledgement that in a program with n components, a developer has 2 to the n possibilities to choose from. One could begin fully untyped, add types to a few modules, and wind up somewhere in the middle of the space of possibilities. We have no data to suggest that developers will avoid certain configurations or gravitate towards others, so the method considers all possibilities. Each gradually typed configuration represents a complete program, so the next step is to measure their running times. Now we have an exponentially large data set, and the challenge is to find a compact summary. First, choose a baseline. The untyped configuration is one possible choice. Second, compute the overhead of each configuration relative to the baseline. From these normalized numbers, it is clear that some configurations have decent performance and others are bad, and so we condense the huge set of running times into one ratio describing the proportion of good configurations. More precisely, we introduce a parameterized measure. A configuration is d-deliverable for some value of d if its running time is no worse than d times the baseline. The idea is that a language implementer can pick a value for d that represents the worst overhead they are willing to impose on users. In summary, start with any program, apply gradual typing, explore all possibilities, and count the proportion of d-deliverable configurations for your chosen value of d. We have also developed a method for plotting the results for a general audience on a two-dimensional axis. On the x-axis, we have values of d from 1 to some large upper bound. On the y-axis, we have the percent of d-deliverable configurations. In the paper, we chose 20x as our upper bound for d. For any program, we can now see how increasing the acceptable overhead along the x-axis increases the proportion of d-deliverable configurations on the y-axis. The line on such a plot should ideally reach the top of the y-axis at a low value of d. But in general, a larger area under the curve is better. One limitation of our method is that it requires an exponential number of measurements. A program with n components implies 2 to the n configurations. To avoid this explosion, we developed a method based on simple random sampling. The idea is to sample a linear number of configurations and then count the proportion of de-deliverable configurations in the sample. Repeating this process for a few samples leads to a statistically significant approximation of the true proportion of de-deliverable configurations. For details and an empirical justification, see the paper. You can also read about an application of the original exhaustive method to typed racket on a suite of 20 benchmark programs, a direct comparison between 3 implementations of typed racket based on the same benchmarks, and an extended discussion of the major performance issues we uncovered. Finally, I want to give a special thanks to Sam Tobin-Hochstadt for developing typed racket and for major improvements that took place alongside this work. This was Ben Greenman explaining the main ideas of our paper. Thanks for listening, and please leave comments on the Journal of Functional Programming webpage. If you have questions, post them too, and I will respond in public.